Okay, guys, so this is a quick introduction to linear regression. And the point we're gonna talk about is we're just gonna go over some of the concepts on this video. Then in the class, I'll start off with a quick summary of the material, and we can get into a little bit more about the statistical tests and a little bit more about how to implement linear regression in SPSS. Okay, so what are we going to do in this chapter? Well, I'm going to start off and I'm going to talk about regression. Now, this week we're focusing on linear regression with a single predictor. So we're kind of concentrating on the simplest possible case of linear regression. And the idea is we can kind of build on that. And in the last week, we're going to look at regression with multiple predictors or independent variables. So we're going to look at how to build a regression model. We're going to look at statistical tests. We're going to look a little bit at, some of the indicators of whether a regression model is a good regression model or not. So we're going to look at the R-squared, which is the variance accounted for. We're going to look at the various tests for showing whether or not a regression is significant. And as I said, we're going to do the regressions in SPSS and learn how to interpret the output. So what is regression? And I'll start off and I'll illustrate this with kind of a quick example. For this example, I'm going to use my Microsoft provided whiteboard. Okay, so imagine that we have, and we'll use the example we've been using in class. We're trying to predict our Y, which is the movie revenue. And that's the movie revenue in the first week of release, or the opening weekend. And for this, we're going to kind of we need an independent variable, which is our X. And this is going to be the social media buzz. Which is going to be, we're going to have tweet rate per hour. Sorry, tweet rate per hour. So how are we going to actually format this? Well, we're going to have our Y. And it's going to be equal to my beta 0 plus beta 1 times my X. Now, each of my Y's and my X's, let's just say it belongs to an item I. And there's also going to be some sort of an error there. So this is the dependent variable. This is going to be the intercept, what we call the intercept. And this is going to be the slope. So, and of course, this is going to be my independent variable. Variable. And this is going to be my error. Okay, so I'm going to see if we can actually now draw this using our tweet rate example. Okay, so what I'm going to do is I'm going to kind of draw this here. So this is going to be my xi. This is going to be kind of my Y eyes. And these guys here, they're just going to be movies. So we have a tweet rate per hour, and we have a revenue. Now, generally, if you look at this, there's going to be some sort of relationship, going back to the kind of the correlation stuff that we did last week. You know, a movie with not much social media buzz is probably not going to get a lot of revenue. And a movie with a lot of social media buzz is probably going to get a lot of revenue. So let's just kind of highlight one of these. We'll highlight this one and say, for example, this could be at the new version, the new avatar coming out. So what we're trying to do here is we're trying to, you know, show this relationship between the movie social media buzz and the actual movie revenue. And what we're doing with regression is we're just trying to build a line of best fit between the X and the Y. So this would be a straight line. I thought this was blue, but it seems to have come out as kind of a rainbow color. But this is like the line of best fit. Now, let's kind of go back to our equation back here. You see here in the equation, we have various things. We have an intercept, we have a slope, and we also have these different errors. So let's just kind of write some of these things on. Beta 0, this is kind of where we meet the y-axis, where x equals 0. So the interpretation here would be the movie revenue for a movie with no buzz. Now, one thing we'll talk about when we make predictions is predictions tend to be less accurate, kind of outside of the realm of much of the data. So if we're kind of extrapolating out of the data, our predictions are not particularly accurate. But so in terms of, you know, if we get a movie with 0 social media buzz, this prediction will not be greatly accurate. We're more accurate kind of here somewhere in the middle. But this is kind of just useful for setting up the regression. And the second thing is, let's just say that over a period, this is the change in Y, all over the change in X. Then my beta 1 is just basically the slope. And as this is a linear regression, the line is straight, then this is going to be the same throughout the whole of the regression. And the final thing, what are my errors? Well, you know, in any business problem, regression is not going to be perfect. So these are just kind of the residuals. I don't like this new version of Microsoft Whiteboard. It's kind of freaking me out. It just adds a load of random junk to it. But these are kind of the residuals. And these are the actual, which I don't like these arrows. These are kind of the errors in the regression, because we're not going to perfectly fit all of these points. So this is kind of just some of the basics of regression. Okay, so we've built this regression model, and this regression model can be used to kind of explain the variables. So here we can explain, you know, how movie revenue is related to social media buzz. And it can also be used for prediction. So if we have a new movie, we can measure the social media buzz in the week before the movie opens. And then we can make a prediction of the movie revenue and utilize that for things like, advertising, concessions, etc. So that is an incredibly basic model of movie revenue. Now, we have a few assumptions that underlie regression. Now, the first one we kind of all know and love. That's the independent random sampling. That happens with pretty much every one of our tests that we do. And note, you can actually build a regression line or a regression model without all of these assumptions, but the statistical tests will not be valid. So for the statistical tests we do, we have certain assumptions. And the first is that, we're randomly sampling. So we're randomly sampling movies from the stream of movies that are coming out. We have normally distributed data, and in particular, we have normally distributed errors. We'll talk more about that when we start looking at this in SPSS. And then the last two I'll draw, we have to have a linear relationship, and we have to have what we call homoscedasticity, or constant variance. So let's kind of go back to our kind of board, and let's have a look at these two things. So what is the linear relationship? Well, let's just see we have an X and a Y. So this is almost going back to the correlation stuff we did last week. We're assuming linearity. So we're assuming this kind of linear relationship, which we can build a regression on. So just draw something like this. And, this would be a linear relationship. We're supposed to be a red tick. And we could, rather than this kind of, remember the curvilinear relationship. So this sort of relationship would not be linear regression. And in fact, if we tried to fit a linear line to this, it would seem that there's no relationship when in fact there is a relationship. It's just not a linear relationship. So we'll put that. So kind of moving on a little bit, heteroskedasticity and homoskedasticity. Let's just move up a little bit. So let's again think about, we've got our let's call it the tweet rate, and we have the revenue here. Now the thing is, imagine we have a movie down here, which is kind of like, maybe it has a revenue of like $1 million. Maybe it's like it's something nobody wants to watch, like the day, a documentary about a business stats professor. And if I'm going to guess the revenue, we have a revenue around $1 million. I'm going to be maybe close. I'm going to be maybe guess $500,000, $1.5 million. So my error is not going to be that big. If I maybe have, for example, Avatar 2 up here, and I'm trying to guess, this could well be like $1 billion. So it may well be that, I'm off by 100 million. And that's homoskedasticity versus heteroskedasticity. So imagine here, as we get bigger movies, my error gets bigger and bigger and bigger and bigger. So let's just draw my regression line. So we start off with small errors, and you see the magnitude of the errors here is pretty small. But as we get kind of bigger, we get much bigger errors occurring. And that's an example of heteroskedasticity. Ideally, what we want is relatively, it doesn't mean all the errors have to be the same, but we need a situation where we have relatively constant errors. So, the magnitude of the errors is relatively constant over time. They don't tend to get bigger or smaller. And okay, this is maybe a little bit too perfect. But you see here the magnitude of the errors at the top is kind of similar to the magnitude of the errors at the bottom. And quite often, if you've got something like, revenue, or you've got distance, or some sort of like numeric scale, you will get heteroscedasticity. So what quite often do is we'll fit both of these variables on a log scale. We'll have a log tweet rate, and we'll have log revenue. And that kind of will often solve the problem. But we'll talk more about that when we do the practical implementation of this stuff. Okay, so let's get a little bit up to the uses of linear regression. We've already talked about prediction and the description explaining relationships, but let's just go through a few uses. So prediction. We might want to, for example, predict movie revenue from social media buzz. We might want to predict house prices from the area of the house. We might want to predict somebody's body mass index from maybe various lifestyle factors, such as, how much fat we eat or how unhealthy the food we has. Or we may want to predict sales revenue based on how much we spend on advertising. So these are all kind of prediction applications. Statistical control, and honestly, I'm not really going to talk about this in the class. It's a little bit beyond the class, where we remove the linear effect of one variable on another. But to give an example, I've done some work on viral videos, and there's specific viral periods where a video really takes off and we can model. But there's also a kind of a linear constant effect over time of just, growing views over time from some sort of baseline, maybe subscribers in your channel. So we could actually build a linear regression and then remove the fitwise from our data to get rid of this linear effect. But honestly, we're not going to focus on this in this. And we can actually have, so thus far I've been talking about empirical examples. So I talked about, movies which are released, they have social media buzz and they have revenue, but we're not really controlling the movie release. But we might want to, for example, determine, a health response based on drug dose. So we might have 10 different quantitative drug doses. Or we might look at different discount levels and see how much product we sold at different discount levels. And just to give you a British example, we may be interested in the taste of tea. So we may see, how much milk we add. We may have 20 different amounts of milk, how that affects the taste of the tea or even the coloration of the tea. Okay, so here's a kind of a quick example. And I put this in because I thought it was kind of cool. Now this has, it isn't a multiple regression, but it has multiple simple linear regressions. We can actually see here, this is like NFL players, the relationship between weight and height. We can see that wide receivers, these people have very little fat. Generally a wide receiver has to be able to run fast. So there is this kind of quite strong relationship between weight and height. But we look at kind of, other kind of positions, for example, offensive tackles, there isn't much of a relationship. And maybe the reason here is an offensive tackle, they're kind of blocking people. They have to be a heavy object and they have to be a certain weight. Most offensive tackles are between like 290 and 350 pounds. And that's the ideal weight. And some of these people are bigger, it's taller, and some are a little bit shorter, but it's not quite as important. So you see here, there's a much flatter less strong relationship between weight and height for offensive tackles. And the same happens here. The smaller positions, the safeties and the cornerbacks, there seems to be a linear, reasonable relationship between weight and height. But we see for defensive ends and defensive tackles, the bigger players, there really isn't that stronger relationship. Okay, so let's kind of summarize what we've done thus far. Then we'll look at how we fit a regression model. We have a dependent variable y, and the dependent variable is what we're trying to predict. We have an independent variable x, which we use to actually predict. So y is the revenue, x is the tweet rate. We have our interceptor, and that's often interpreted as the value of y when x equals 0. So our predicted revenue when we have 0 social media buzz. We have the beta 1. This is the slope or intercept. And this is often interpreted as the increase in y for every increase in 1 of x. So if my social media buzz increases by 1 unit, 1 tweet per hour, then this is the increase in revenue in millions of dollars, predicted rate of increase in revenue. And as I said, we have an error term because our regression, any business regression, is never going to be perfect. Okay, and just a few simple examples from the book. These are really toy examples. Here we've got an example where we've got 2 regression lines. Our beta 0 is the same, but the beta 1 is different. Here on the red line, the beta 1 is positive, and in the green line, the beta 1 is negative. And here in the second graph, we have 3 different regression lines. In all of these, the beta 1 is the same because the slope is the same, but we have 3 different beta 0s. Okay, so I'll talk a little bit to finish the video about the process of regression. Okay, so we had this idea of a regression model, and I'll draw this beautiful circle here, and we're going to have a regression model. And we've got a y equals beta 0 plus beta 1 x plus the error. And then we have a regression equation and basically all this is doing is we're saying that the mean of the y without the error is basically beta 0 plus beta 1 x. So this is without any error, we have a regression line plus we have error. So this is just kind of a very conceptual kind of definition of a regression line. And we know that we have 2 unknown parameters. Which are beta 0 and beta 1. Now, we have our model, but what do we need next? Well, we need some actual data. Let me just remove that accidental note. Okay, so we have some actual data. Another beautiful circle. And in our data, we have an x and a y. And then we have all these data points. And this is just saying kind of I equals 1 to n. So we have n movies and there's we have n tweet rates and n revenue. So when I showed you the tweet rate example, we had 2 columns. We had the tweet rate per hour and the revenue. That's just basically our sample data set. And what we're doing is we now estimate the regression equation. Let's move it up a little bit. So we're trying to estimate the regression equation. And here we're going to have our y hat equals beta 0 hat plus beta 1 hat x. Now all this means is the hat is basically means we've fitted a value to our equation using the data. So when we have the data, the hat is basically the fitted line. And this is kind of our model in theory, and this is our model in practice where we fit the data. And here we have our sample statistics. So beta hat 0 and beta hat 1. So this looks a lot like when we did the t-tests and the z-tests. Rather than a mu and an x bar, we've got the beta 1, which is the unknown population parameter, and beta 1, and the beta hat 0, which we calculate from the data, and the beta hat 1 that we also calculate in the data. And so kind of go to the final stage, where we create a circle. And basically the beta hat 0 and beta hat 1 are used to provide inference on beta 0 and beta 1. So, you know, we're going to talk about this next kind of in the class, but for example, we might want to actually prove this hypothesis that the slope, and there's actually meaningful regression, i.e. the slope isn't flat, there's a regression line that shows an absolute relationship. So we're going to use these kind of beta hat 0 and beta hat 1 values to kind of actually prove hypotheses on beta 1. Now, we could actually have something for beta 0, but it's not really meaningful about the regression. It's just purely the intercept. We're not usually interested in proving hypotheses on the